Imagine standing beneath a perfectly clear night sky. Above you are thousands of stars scattered across the darkness. Some are relatively close, perhaps only a few dozen light years away. Others are so distant that the light entering your eyes tonight began its journey before human civilization existed. Some of the faintest objects visible through powerful telescopes are so far away that their light started traveling toward Earth when the universe was only a fraction of its current age. Entire chapters of cosmic history unfolded while those photons crossed the void. Galaxies formed, stars exploded, black holes grew, planets emerged, life evolved. Human beings learned to build cities, write books, and ask questions about the universe. Through all of that immense history, light continued moving through space. At least, that is how it appears to us. But what if that picture is incomplete? What if one of the most familiar assumptions we make about light is fundamentally wrong? What if light does not actually experience its journey the way we imagine? This possibility sounds absurd at first because we instinctively think of motion as something that requires time. Every journey we have ever taken unfolds through duration. Walking across a room takes time. Driving across a country takes time. Flying across an ocean takes time. Even the fastest spacecraft humanity has ever built require years or decades to cross the vast distances of our solar system. Movement and time seem inseparable. One implies the other. To travel from one location to another means existing during the interval between departure and arrival. Yet light occupies a position unlike anything else in nature. Light does not merely move quickly, it moves at the maximum speed permitted by reality itself. Nothing carrying mass can reach it. No object can overtake it. No signal can surpass it. The speed of light is not simply a high speed among many possible speeds. It appears to be a fundamental property woven directly into the structure of spacetime. The universe itself seems organized around this limit. For centuries, nobody understood just how strange that fact really was. Light appeared mysterious, but not fundamentally different from other moving things. Then, in the early 20th century, Einstein transformed our understanding of reality forever. His theory of relativity revealed that space and time are not fixed backgrounds against which events occur. They are dynamic aspects of a deeper structure. They stretch, they contract, they change depending on motion, and most importantly, they behave in extraordinary ways as objects approach the speed of light. The implications were so bizarre that even today they feel almost impossible to accept intuitively. Imagine a future spacecraft capable of traveling at 90% the speed of light. To the astronauts on board, life would appear relatively normal. Their clocks would tick, their hearts would beat, conversations would occur normally. Nothing about their local experience would feel unusual. Yet observers watching from Earth would see something remarkable. The clocks on board the spacecraft would appear to run slower. Every process aboard the ship would seem slightly delayed. Time itself would be stretching. Push the speed higher, and the effect becomes increasingly dramatic. At 99% of light speed, the slowing becomes enormous. At 99.99%, it becomes extraordinary. A journey that appears to last only months for the travelers might correspond to years, decades, or even centuries elsewhere. Time itself begins separating between different observers. This is not science fiction. It is not speculation. Time dilation has been measured repeatedly in experiments. Atomic clocks carried aboard aircraft drift relative to clocks on the ground. Particles created in accelerators survive far longer than they otherwise should because time slows for them at high speeds. GPS satellites must constantly account for relativistic effects, or their navigation systems would quickly become inaccurate. Reality genuinely behaves this way. The closer something moves to light speed, the slower time passes for it relative to the outside universe. And then comes the astonishing conclusion, hiding at the end of that trend. What happens if something actually travels at the speed of light? The equations point toward a startling answer. The passage of time shrinks toward zero. Now, physicists must be careful here. Relativity does not allow us to simply sit on a photon and observe the universe from its perspective. Strictly speaking, light does not possess a conventional reference frame. Nevertheless, the mathematics reveals something profound. As velocity approaches the speed of light, experienced time approaches nothing at all. The consequences are almost impossible to visualize. Consider a photon born inside a distant star. Perhaps that star lies 1,000 light years from Earth. From our perspective, the photon begins a vast voyage through space. It travels across interstellar darkness for an entire millennium. Generations rise and fall. Nations appear and disappear. Languages evolve. Human history unfolds. Yet eventually, one night, that photon reaches Earth and enters someone's eye. To us, 1,000 years have passed. For the light itself, something far stranger seems to occur. There is no millennium, no centuries, no years, no waiting. The emission and the absorption become directly connected. Departure and arrival are not separated by an experience duration. The journey effectively collapses, and suddenly, one of the most familiar ideas in existence begins to break apart. Because our understanding of reality depends completely upon time, every memory you possess exists because time passes. Every plan you make depends upon future moments not yet arriving. Every aspect of your identity is built from a sequence of experiences stretching backward into the past. You know who you are because yesterday exists. In a way, tomorrow does not. But if light experiences no passage of time, then concepts like past and future lose their meaning. A photon leaving a star and a photon arriving at a detector become part of the same timeless connection. This is not merely strange, it is deeply unsettling. Think about what it means for something to have no future. Everything in your life has a future. Tomorrow exists as a possibility. Next week exists as a possibility. Your plans, hopes, fears, and expectations all depend upon the existence of future moments. Likewise, everything in your life has a past. Memories accumulate behind you. History stretches backward. Experience forms a chain connecting one moment to the next. Light may possess neither. No future because no time remains ahead. No past because no time exists behind. Only the event itself. Only the connection. Only the path through spacetime. The deeper physicists explored this idea, the more they realized that light occupies a unique position within reality. It sits on the boundary between concepts that make sense for ordinary matter and concepts that begin breaking down entirely. Light obeys the laws of spacetime while simultaneously revealing how strange those laws truly are. It acts as both a participant in the universe and a messenger, carrying information across unimaginable distances. Every image you have ever seen depended on photons. Every observation astronomers make depends on photons. Every glimpse of the distant cosmos arrives through photons. And yet those same photons may not experience the universe in the way we do at all. This realization leads to an even deeper question. If light does not experience time, what exactly is time in the first place? Perhaps our understanding of temporal flow is more limited than we realize. Perhaps past and future are not as fundamental as they appear. Perhaps the universe contains a deeper structure hidden beneath our everyday experience, a structure that becomes visible only when we examine reality at its most extreme limits. Because as Einstein continued exploring relativity, he discovered something even more astonishing than time dilation. Not only does time slow near light speed, space itself begins to change as well. Distances shrink, journeys compress, the universe transforms. And in the next chapter, we will discover why the cosmos looks radically different as you approach the speed of light, and why a photon's journey across billions of light years may be far stranger than anyone ever imagined. The deeper we follow this idea, the more it begins to challenge something we rarely question. Most of us assume that distance is a real, objective property of the universe. We imagine the stars sitting in fixed locations separated by measurable gaps. We imagine galaxies occupying particular regions of space. We imagine the cosmos itself as a gigantic, three-dimensional stage upon which everything unfolds. It feels natural to think this way because it matches our everyday experience. The distance between two buildings does not depend on how quickly you walk between them. The distance between two cities does not depend on the speed of your car. The distance between Earth and the Moon does not seem to change depending on who measures it. Yet relativity reveals that these assumptions are only approximately true. They work well for creatures moving at ordinary speeds, but they begin to break down as velocity approaches the cosmic speed limit. Space itself becomes flexible. Distance becomes negotiable. The universe ceases to be the rigid structure our intuition expects. To appreciate how radical this is, imagine that humanity eventually develops a spacecraft capable of traveling at 99.999999% of the speed of light. Such a machine lies far beyond our current technology, but physics allows us to imagine it. Suppose a crew boards this vessel and sets course for a galaxy located millions of light years away. From Earth's perspective, the mission appears absurd. Even at nearly the speed of light, the journey would require millions of years. Long before the travelers arrived, every nation currently existing on Earth would vanish. Entire branches of civilization would evolve into forms we cannot predict. Oceans would shift, continents would move, the night sky itself would slowly change. The galaxy toward which the travelers are heading might even evolve significantly during the voyage. To observers remaining behind, the mission appears hopelessly long, but aboard the spacecraft, something profoundly different occurs. As velocity climbs closer and closer to light speed, the universe begins compressing in the direction of travel. The distance between departure and destination shrinks, not visually, not psychologically, physically, mathematically. The travelers do not merely move faster through space. The amount of space they must cross decreases. The galaxy ahead begins drawing closer in a very literal sense. Distances that once seemed impossible begin collapsing. The larger the velocity becomes, the more dramatic the effect. Eventually, the vast gulf separating galaxies may become far smaller from the traveler's perspective than anyone on Earth would consider possible. This is where relativity starts feeling less like physics and more like something pulled from a dream. We are accustomed to thinking of movement as crossing a fixed landscape. Relativity reverses that intuition. At extreme speeds, the landscape itself changes. Space participates in the journey. The universe actively reshapes itself around motion. And if we continue following this process all the way to its limit, something extraordinary emerges. Because light does not travel at 99% of its maximum speed. or 99.9%, or 99.999999%. Light exists exactly at the limit, the very edge, the point where relativity reaches its most extreme form. And at that boundary, the implications become almost impossible to visualize. Consider again a photon born inside a distant star. Perhaps that star exists on the opposite side of the Milky Way. Perhaps it exists in another galaxy entirely. Perhaps it belongs to a quasar whose light began traveling toward us before Earth even existed. To us, the journey appears immense. The photon crosses distances measured in trillions upon trillions of kilometers. Entire epochs pass while it travels. Geological ages come and go. Species emerge and vanish. Stars are born and die. Black holes consume matter. Galaxies drift through expanding space. Cosmic history unfolds while the photon continues moving. Yet the closer we examine the mathematics, the stranger the situation becomes. From the perspective suggested by relativity, the distance separating emission from absorption shrinks toward nothing. Think carefully about what that means. The photon does not need to endure billions of years because there are no billions of years to endure. The photon does not need to cross billions of light years because there are no billions of light years to cross. The concepts themselves begin collapsing. Journey and destination start merging into a single structure. Departure and arrival become inseparable. For us, the photon appears to travel. For the underlying geometry of spacetime, something much stranger may be happening. This realization has fascinated physicists for generations because it hints at a universe that looks fundamentally different from the one we experience. Human beings live in a reality defined by separation. We are separated from tomorrow by time. We are separated from distant stars by space. We are separated from our past by memory and from our future by uncertainty. Our entire existence is built upon intervals. Everything meaningful in life unfolds across gaps. We wait for things. We anticipate things. We remember things. Our consciousness itself appears to move through time, carrying us from one moment to the next. Light may not participate in any of that. And if light does not participate, then perhaps some of our deepest assumptions about reality are not fundamental after all. Perhaps the universe is not truly divided into separate moments. Perhaps it only appears that way to creatures like us. This possibility becomes even more intriguing when we consider one of Einstein's most revolutionary insights. Relativity does not describe space and time as separate entities. Instead, it combines them into a single structure known as spacetime. In everyday life, we treat distance and duration as different things. We ask how far something is. We ask how long something takes. These seem like distinct questions, but relativity reveals that space and time are deeply interconnected. Change one, and the other changes too. The universe preserves the speed of light by continuously adjusting the balance between spatial separation and temporal separation. This means that when time shrinks, space shrinks as well. When space stretches, time responds. The two are woven together into a single cosmic fabric, and light exists at the point where that fabric reaches its most extreme behavior. Imagine stretching a rubber sheet. Patterns appear. Distances change. Shapes distort. Now imagine that the sheet represents space-time itself. Massive objects bend it through gravity. Motion reshapes it through relativity. Everything in the universe exists within this flexible geometry. Yet light occupies a unique position because it travels along the very paths that define the structure of spacetime. In a sense, light traces the skeleton of reality itself. This is one reason light plays such a central role in modern physics. Whenever scientists push their understanding to the deepest levels, light appears. The speed of light defines causality. The speed of light appears in relativity. The speed of light helps determine how information moves through the cosmos. The speed of light influences black holes, cosmology, quantum theory, and the expansion of the universe. Again and again, the study of light becomes the study of reality. And nowhere is this more evident than in the strange disappearance of distance and duration as we approach light speed. At first, this sounds like a mathematical curiosity, an odd consequence of equations. But the deeper you think about it, the more profound it becomes. Because if space and time both collapse for light, then one of the most basic features of our experience may not exist at the deepest level of reality: separation. The universe feels divided into here and there, now and then, past and future. Yet light hints that these distinctions may not be absolute. They may emerge only for observers moving below the cosmic speed limit. The faster one approaches light speed, the more these divisions begin dissolving. And at the limit itself, something astonishing seems to happen. The distinction between beginning and ending starts to disappear. The distinction between origin and destination starts to disappear. The distinction between past and future starts to disappear, which raises a question so strange that it has puzzled scientists, philosophers, and science enthusiasts for decades. If a photon experiences no passage of time and no meaningful distance, what does the universe actually look like from the edge of light itself? And more importantly, can that question even make sense? Because in the next chapter, we are going to confront one of the most mind-bending ideas in modern physics: the possibility that asking what a photon sees may reveal something profound not only about light, but about the nature of reality itself. Few questions in all of physics have inspired more curiosity than this one. It sounds simple enough to ask, yet the deeper we investigate it, the stranger it becomes. If you could somehow ride alongside a beam of light, what would the universe look like? What would a photon actually see during its journey through the cosmos? For most people, the answer seems like it should involve some extraordinary visual experience. Perhaps distant galaxies would blur past at impossible speeds. Perhaps stars would stretch into glowing lines. Perhaps the entire history of the universe would unfold in an instant. After all, if light travels faster than anything else in existence, surely its view of reality must be the most extreme perspective imaginable. What makes this question especially fascinating is that it is remarkably similar to one that obsessed a young Albert Einstein long before he became famous. As a teenager, Einstein often imagined himself chasing a beam of light through space. He wondered what would happen if he could somehow catch up to it. Suppose he accelerated faster and faster until he matched the speed of the beam. Would the light freeze in front of him like a motionless wave? Would time stop? Would the universe look different? These thought experiments haunted him for years. Eventually, they helped inspire the theory of special relativity, one of the greatest scientific achievements in human history. Yet the irony is that the deeper relativity developed, the more it suggested that the original question might not have an answer at all. Not because it is too difficult to calculate, but because the assumptions hidden inside the question begin to break down. The problem starts with something we rarely think about. Every experience you have ever had depends upon the passage of time. Every sight, every sound, every memory, every thought requires a sequence of events. Even the act of seeing depends on time. Light enters your eyes. Signals travel through your nervous system. Your brain processes information. conscious awareness emerges. The entire process unfolds across a tiny interval of time. It happens so quickly that it feels instantaneous, but it is not. Experience itself is built upon change, and change requires duration. Imagine trying to watch a movie without any passage of time. The frames could exist, but they would never transition from one to the next. No story would unfold. No movement would occur. No experience would be possible. The very concept of observation assumes a before and an after. This is where things become strange for light, because according to relativity, the closer something moves to the speed of light, the more time slows down relative to the outside universe. At ordinary speeds, the effect is tiny. At extreme speeds, it becomes enormous. And at the limit occupied by light itself, the passage of time approaches zero. This leads to a remarkable conclusion. If time does not pass, then experience, as we understand it, becomes impossible. There are no moments to compare, no sequence of events, no flow of information, no progression from one state to another. This is why physicists often say that asking what a photon sees is like asking what the number 3 tastes like. The question sounds meaningful at first, but the concepts involved may not belong together. Seeing requires time. A photon exists at the boundary where time loses its ordinary meaning. Yet the temptation to keep asking remains irresistible because the implications are so profound. Imagine a photon emitted from a star on the far side of the observable universe. To us, the journey takes billions of years. The photon leaves its source long before Earth forms. It travels while galaxies collide and stars are born. It crosses an expanding universe. Eventually, after an almost incomprehensible voyage, it reaches a telescope. From our perspective, the journey spans vast stretches of cosmic history. But from the perspective implied by relativity, no time passes. The departure and arrival become directly connected. The billions of years separating them disappear, not because the photon travels infinitely fast, but because time itself ceases to create a meaningful interval between the two events. Pause for a moment and think about how strange this really is. Every story you have ever known depends upon time. Every journey depends upon time. Every achievement, every relationship, every civilization, every star, every galaxy evolves through time. Yet light appears to occupy a unique position where those distinctions begin dissolving. A photon emitted shortly after the Big Bang and absorbed billions of years later may be connected by no experienced duration at all. To us, cosmic history unfolds between those events. To light, the separation vanishes. This realization has led some physicists and philosophers to wonder whether our experience of time is more limited than we realize. Perhaps the universe does not fundamentally unfold moment by moment. Perhaps that sensation emerges because we are slow-moving creatures trapped far below the speed of light. Imagine an ant crawling across a gigantic painting. It experiences only a tiny patch at any given moment. It gradually discovers the image piece by piece. The ant naturally assumes the picture is being revealed over time. Yet from a higher perspective, the entire painting already exists. Some interpretations of relativity suggest reality itself may be similar. We experience existence sequentially because of the way consciousness moves through spacetime, not because spacetime itself is continuously being created. This idea becomes even more intriguing when we examine what relativity says about distance. Earlier, we discovered that space contracts as velocity increases. The faster something moves, the shorter distances become along its direction of travel. At everyday speeds, the effect is negligible. At relativistic speeds, it becomes dramatic. Near light speed, enormous cosmic distances shrink. A galaxy millions of light years away may appear vastly closer from the perspective of a near light speed traveler. Continue pushing toward the ultimate limit, and the contraction becomes more extreme. The separation between origin and destination approaches zero. This means that for light, not only does time disappear, but distance itself begins losing meaning. The photon does not merely avoid aging. The universe itself compresses. Space and time both collapse together. The result is one of the strangest ideas in all of modern science. From the perspective suggested by relativity, the photon's journey effectively disappears. The path remains visible to us. We can measure it, we can calculate it, we can describe it. Yet, at the deepest level, the distinction between departure and arrival begins fading away. This raises an extraordinary possibility. Perhaps the universe is far more connected than our ordinary experience suggests. Human beings naturally think in terms of separation. We separate past from future. We separate here from there. We separate cause from effect. We separate ourselves from distant stars. Yet light repeatedly hints that these divisions may not be fundamental. Every photon forms a connection between events. A star emits light. A planet receives it. A galaxy shines. A telescope records it. Information moves across space-time, linking distant regions of reality. The deeper we investigate, the less photons resemble tiny objects racing through empty space, and the more they resemble threads stitching the cosmos together. They connect the birth of stars to the eyes of observers. They connect ancient events to present awareness. They connect distant corners of the universe into a single coherent structure. In a sense, every photon is a bridge, and perhaps that is why light plays such a central role in physics. Again and again, whenever scientists push toward the deepest layers of reality, light appears waiting for them. Relativity revolves around the speed of light. Astronomy depends on light. Quantum mechanics emerged partly from attempts to understand light. Cosmology relies upon light arriving from the distant universe. Even our understanding of space and time themselves is inseparable from light. It is almost as though light occupies a special position within existence, sitting at the boundary between ordinary experience and the deeper structure hidden beneath it. The more closely we examine it, the more our assumptions begin falling apart. Time becomes flexible. Distance becomes flexible. Separation becomes questionable. The universe reveals itself as something far stranger than common sense ever imagined. And yet the mystery continues growing. Because if light experiences no time, then another question immediately appears. We often say that people age because time passes. Stars age because time passes. Galaxies evolve because time passes. Everything in the universe seems trapped within the relentless flow of time. But if light exists outside that flow, then what happens to a photon over the course of billions of years? Does it age? Does it change? Does it experience the history of the cosmos in any meaningful sense at all? The answer will take us even deeper into the nature of space-time itself. And in the next chapter, we will discover why a photon born at the beginning of the universe may be just as young today as the moment it first emerged into the light. Everything you have ever known exists inside time. Every person you have ever met is changing from moment to moment. Your body is not the same body you possessed 10 years ago. The cells have changed. The molecules have changed. Even the atoms themselves participate in a constant dance of interaction and replacement. Mountains slowly erode. Oceans reshape coastlines. Stars consume their fuel. Galaxies evolve over billions of years. Everywhere we look, existence appears inseparable from aging. To exist is to change, and to change is to move through time. It feels so obvious that we rarely stop to question it. Yet hidden within the behavior of light is a possibility so strange that it forces us to reconsider one of the most fundamental assumptions we make about reality. What if something could exist without aging at all? What if something could travel across the entire observable universe and remain exactly as young as the moment it was born? At first glance, this seems impossible. Aging appears unavoidable. Even the most stable objects eventually change. Radioactive atoms decay. Stars exhaust their nuclear fuel. Black holes slowly evaporate. Given enough time, everything seems subject to transformation. Time acts like a universal river, carrying all things forward whether they wish to go or not. Nothing escapes its current. Nothing remains untouched. Yet photons appear to occupy a unique position. They are not merely moving very quickly through time. According to relativity, they may not be moving through time at all in the ordinary sense. And if that is true, then the entire concept of aging becomes deeply problematic. Think about what aging actually means. We usually imagine it as a process occurring because time passes. A child becomes an adult becomes elderly, a star becomes a red giant. The process requires duration. One state transforms into another because moments accumulate. Aging is not a thing separate from time. Aging is what happens when time acts upon a system. Remove the passage of time and the mechanism itself begins disappearing. A clock cannot advance if no moments separate one tick from the next. A tree cannot grow if no duration exists between seed and forest. A civilization cannot develop if history never unfolds. Aging depends completely upon temporal intervals. This is what makes light so fascinating. Imagine a photon emitted from the surface of a distant star. Perhaps the star lies within our galaxy. Perhaps it belongs to a galaxy so remote that its light began traveling before Earth formed. From our perspective, the photon embarks upon a vast cosmic journey. It crosses unimaginable distances. It passes through interstellar clouds. It travels between galaxies. It survives while stars explode and black holes merge. Billions of years may pass before it finally reaches a detector. To us, the photon appears ancient. We naturally imagine it as a traveler enduring an immense voyage through the history of the cosmos. But relativity tells a different story. The closer we examine the mathematics, the less meaningful that immense duration becomes. As velocity approaches the speed of light, experience time shrinks. Near light speed, years become months. Months become days. Days become moments. At the limit occupied by light itself, the interval approaches zero. The photon does not experience billions of years because there are no billions of years to experience. The departure and arrival remain connected by no passage of time at all. From the photon's perspective, or more accurately, from the perspective implied by relativity, the universe does not age around it. The journey does not unfold. The cosmic history separating emission and absorption disappears. This creates one of the strangest conclusions in modern physics. A photon emitted shortly after the Big Bang may be just as young today as it was when it first emerged into existence. Consider the cosmic microwave background, the oldest light we can observe. These photons were released roughly 380,000 years after the Big Bang, long before stars, planets, or galaxies resembled the structures we see today. They have been traveling through space for approximately 13.8 billion years. During that time, the universe expanded dramatically. Galaxies formed and evolved. Entire generations of stars lived and died. Heavy elements emerged. Planets appeared. Life arose. Human civilization developed. The amount of cosmic history separating their emission from their detection is almost beyond comprehension. Yet, from the perspective suggested by relativity, those photons never experienced any of it. The billions of years belong to us, not to them. This is one of those ideas that sounds simple until you truly sit with it. Imagine receiving a letter from someone who lived 13 billion years ago. The sender exists in a universe almost unrecognizable compared to ours. The cosmos itself has changed beyond measure. Yet the messenger carrying that information experiences no interval between departure and arrival. To the messenger, the beginning and ending remain directly connected. It is almost as though the photon steps outside history while simultaneously allowing history to be observed. The deeper we think about this, the stranger it becomes. Human beings define age through accumulated experience. A person who has lived 80 years possesses memories stretching across decades. Their identity reflects countless moments layered upon one another. Age is not merely a number, it is a record of temporal passage. But a photon accumulates nothing. It gathers no memories. It acquires no scars. It records no history. It possesses no sequence of experiences through which change can occur. The very framework required for aging is absent, and yet photons are not frozen objects. They still participate in reality. They carry energy. They carry information. They influence matter. They help shape the visible universe. Light from distant stars allows us to see across cosmic distances. Light from the early universe allows cosmologists to study ancient history. Light entering your eyes right now allows you to perceive the world around you. Photons remain active participants in existence, despite apparently existing outside one of the most fundamental processes we associate with existence itself. This raises a profound question. If aging depends on time, and light does not experience time, then perhaps age itself is not as fundamental as we assume. Maybe aging is not an intrinsic property of objects. Maybe it emerges from the relationship between objects and spacetime. A mountain ages because it exists within time. A star ages because nuclear reactions unfold through time. Human beings age because biological processes occur through time. But light occupies a unique position where those temporal processes cease to operate normally. The photon becomes a glimpse into a reality where age loses its meaning. This realization also changes how we think about the universe itself. We often imagine the cosmos as a vast historical narrative. The Big Bang occurs, galaxies form, stars ignite, life emerges. Everything unfolds through a sequence of events. And from our perspective, that picture is absolutely correct. Yet photons reveal another layer beneath it. They hint that the universe may contain connections transcending ordinary temporal separation. Events billions of years apart become directly linked through light. Ancient stars communicate with present observers. The earliest moments of cosmic history remain connected to modern telescopes. Reality begins looking less like isolated moments and more like an interconnected structure stitched together by photons. Perhaps this is why light occupies such a special place in physics. Again and again, whenever we approach the deepest questions about space, time, and existence, light is already waiting there. It challenges our assumptions. It reveals hidden layers beneath common sense. It forces us to confront possibilities that feel almost impossible to imagine. And one of the most remarkable possibilities is this. The universe's fastest messenger may be forever young. A photon born billions of years ago remains untouched by the immense history that unfolded during its journey. It does not age. It does not wait. It does not move through time the way we do. Instead, it exists at the edge of a reality where the distinction between beginning and ending becomes increasingly difficult to define. And that leads directly to an even deeper mystery. Because if light never ages, then what does that mean for the universe itself? What does it mean for a cosmos whose most important messenger exists outside ordinary temporal experience? And perhaps most intriguingly of all, what happens when light encounters the most extreme distortions of spacetime in existence, black holes, where time itself begins behaving in ways even stranger than those experienced by photons? In the next chapter, we will follow light toward the edge of a black hole and discover why the relationship between photons and gravity may reveal some of the deepest secrets hidden within the fabric of reality itself. Few objects in the universe challenge our understanding of reality more completely than black holes. They are often described as cosmic monsters, regions of space where gravity becomes so powerful that nothing can escape. Not planets, not stars, not spacecraft, not even light itself. Yet, while this description is technically correct, it barely hints at how strange black holes truly are. The deeper physicists have investigated them, the more black holes have transformed from astronomical curiosities into laboratories for some of the deepest questions in existence. Questions about time, questions about information, questions about reality itself. And perhaps nowhere do these mysteries become more fascinating than when light approaches the edge of a black hole. Imagine a photon beginning its journey somewhere far from any strong gravitational field. Perhaps it leaves the surface of a star much like our sun. At first, everything appears normal. The photon moves through space at the speed of light. Distances are crossed. Information is carried. The universe behaves according to the familiar rules of relativity. But eventually, the photon approaches a black hole. At first, the effects are subtle. Gravity bends its path slightly. This phenomenon, known as gravitational lensing, allows black holes to distort the appearance of distant objects. Light that would normally travel in straight lines begins curving through space-time. Entire galaxies can appear stretched, duplicated, or warped because their light passed near massive objects on its way toward us. Even before reaching a black hole, light starts revealing an extraordinary truth about gravity. Gravity is not simply a force pulling objects through space. According to Einstein, gravity is geometry itself. Massive objects reshape spacetime, and light follows the resulting curves. The closer the photon moves toward the black hole, the more dramatic these distortions become. Space bends. Time bends. The entire structure of reality begins twisting into forms that seem almost impossible from an everyday perspective. To understand why, imagine placing a heavy metal ball on a stretched rubber sheet. The sheet sags inward. Smaller objects rolling nearby naturally curve toward the depression. This popular analogy is often used to explain gravity, though the real situation is far more complex. A black hole does not merely create a small dent in spacetime. It creates one of the most extreme distortions known in nature. The geometry becomes so warped that all paths eventually point inward. Moving away becomes as impossible as moving backward through time. This is where the famous event horizon appears. The event horizon is often imagined as a physical surface surrounding a black hole, but that picture can be misleading. It is not a wall. It is not a barrier made of matter. It is a boundary within space-time itself. Cross it, and every possible future leads deeper into the black hole. The situation is difficult to visualize because our intuition evolved in environments where space and time behave normally. Near an event horizon, those intuitions begin failing. The distinction between moving through space and moving through time becomes increasingly blurred. The future itself points inward. Now imagine watching a photon approach that horizon from a safe distance. Something remarkable happens. As the photon falls deeper into the black hole's gravitational field, its light becomes increasingly stretched. The wavelength grows longer. The energy decreases. The photon becomes redder and dimmer. Physicists call this gravitational redshift. The stronger the gravity, the more extreme the effect becomes. To a distant observer, the photon appears to slow down, not because it actually moves slower than light. It never does. But because time itself behaves differently near the black hole. Clocks close to the horizon tick more slowly relative to clocks farther away. This phenomenon, known as gravitational time dilation, has been confirmed repeatedly through experiments. Even GPS satellites experience tiny versions of it, but near a black hole, the effect becomes extraordinary. Imagine a clock falling toward the event horizon. To someone traveling alongside the clock, everything seems normal. The seconds pass. The mechanism functions. Nothing unusual appears to happen locally. But to an observer watching from far away, the clock slows. The closer it gets to the horizon, the slower it appears. Eventually, the ticking nearly stops altogether. The observer never sees the clock cross the horizon. Instead, it appears frozen at the edge of the black hole, fading and reddening until it becomes effectively invisible. This is one of the strangest consequences of relativity. From the perspective of the distant observer, time itself seems to stop near the horizon. Think about what this means for light. Earlier, we discovered that photons already occupy a unique relationship with time. The passage of time shrinks toward zero along their journeys. Light appears to exist at the boundary where temporal intervals collapse. Now place that same light near a black hole, where gravity itself slows time to extraordinary degrees. Suddenly, two of the strangest features of modern physics intersect. The object that experiences no passage of time encounters a region where time itself becomes distorted beyond ordinary comprehension. The result is a reality that feels almost dreamlike. Imagine a photon emitted just outside the event horizon. To the photon, no time passes. Its emission and absorption remain directly connected. Yet, to a distant observer, the photon's escape becomes increasingly difficult. The light loses energy. Its wavelength stretches. The black hole's gravity seems to trap it. The same event acquires two radically different descriptions depending on perspective. Neither description is wrong. Both emerge naturally from relativity. Reality itself becomes dependent on the observer's position within spacetime. This realization disturbed many physicists when they first encountered it. We are accustomed to believing that events possess a single objective description. Something either happens or it does not. A clock either ticks or it does not. A journey either occurs or it does not. Relativity forces us to abandon these assumptions. Different observers can disagree about durations, distances, and sequences of events while remaining equally correct. Near black holes, these disagreements become so extreme that reality begins resembling multiple, overlapping narratives rather than a single universal story. And yet the mystery deepens further, because black holes do not merely distort time. They challenge our understanding of information itself. Every photon carries information. Light arriving from a star tells us about the star's temperature, composition, motion, and history. Light acts as the universe's messenger. Through photons, distant events become observable. Astronomy is possible because information travels through light. But what happens when that information falls into a black hole? For decades, physicists struggled with this question. If a photon carrying information crosses the event horizon, does the information disappear forever? Classical descriptions of black holes seem to suggest exactly that. Information falls inward and becomes inaccessible. Yet quantum mechanics strongly suggests that information cannot simply vanish. The laws governing quantum systems preserve information. This conflict created one of the greatest puzzles in modern physics, the black hole information paradox. The paradox transformed black holes from astronomical objects into profound theoretical mysteries. Suddenly, the question was not merely what black holes do to matter or light. The question became what black holes reveal about the foundations of reality itself. If information can be destroyed, quantum theory faces a serious problem. If information survives, then our understanding of black holes must be incomplete. Some of the greatest physicists of the last half-century devoted their careers to this puzzle. Entire theories emerged in response. Ideas involving holographic universes, quantum entanglement, and the deep structure of spacetime itself began appearing. Once again, light stood at the center of the mystery, because every attempt to understand black holes eventually becomes an attempt to understand photons. The messenger reveals the limitations of our theories. The messenger exposes the cracks in our understanding. And perhaps most intriguingly, the messenger hints that space, time, gravity, and information may all be connected at a level far deeper than we currently comprehend. As we continue our journey, the picture becomes increasingly extraordinary. Light may not age. Light may not experience time. Light may become trapped by gravity. Light may carry the information from which our understanding of the universe is built. Yet the deepest mystery still lies ahead, because if photons can survive billions of years without aging, and if black holes can distort space-time itself, then what happens to light on the largest scales imaginable? What happens to the oldest photons in existence? What happens to light as the universe approaches its final future? To answer that question, we must leave black holes behind and travel outward once more, beyond galaxies, beyond clusters, beyond the observable structures of the cosmos, toward the ultimate fate of light itself. When most people think about ancient things, they imagine old civilizations, fossilized remains of extinct creatures, or perhaps stars that have been shining for billions of years. Human history stretches back a few thousand years. The oldest trees on Earth have survived for several millennia. Entire mountain ranges have existed for hundreds of millions of years. Compared to the timescales of everyday life, these numbers feel almost unimaginable. Yet, from the perspective of the cosmos, they are astonishingly small. The universe itself is approximately 13.8 billion years old, and hidden throughout that immense span of time is something extraordinary. There are photons reaching us today that have been traveling for nearly the entire history of existence. Light so ancient that it began its journey long before Earth formed, long before the sun existed, long before galaxies resembled the structures we see today. If any light could be called old, surely it would be this light. And yet, in one of the strangest twists in all of physics, those photons may be completely ageless. To understand why, we need to travel back to an era unlike anything that exists today, a time before planets, before stars, before galaxies, before darkness itself. The earliest universe was not filled with isolated objects floating through empty space. Instead, it resembled a vast ocean of energy and particles. Temperatures were so extreme that atoms could not exist. Electrons moved freely. Photons constantly collided with charged particles. Light could not travel significant distances because the universe was opaque. Imagine trying to shine a flashlight through the center of a star. The light would not travel far before interacting with surrounding matter. The early universe behaved similarly. Everywhere photons attempted to move, they immediately encountered particles blocking their path. For hundreds of thousands of years after the Big Bang, the universe remained trapped in this state. Then something remarkable happened. As space expanded, temperatures gradually fell. Eventually, the cosmos cooled enough for electrons and atomic nuclei to combine into stable atoms. Suddenly, the constant scattering of photons decreased dramatically. Light became free to travel. The universe, for the first time, became transparent. And in that moment, a vast flood of radiation was released into space. Those photons are still traveling today. Every direction we look in the sky contains them. They fill the entire universe. They surround Earth right now. This ancient radiation is known as the cosmic microwave background, and it represents the oldest light humanity has ever observed. When astronomers detect these photons, they are effectively looking back almost to the beginning of time itself. Not quite the Big Bang, but astonishingly close. The cosmic microwave background is often described as the afterglow of creation, a fossil from the infancy of the universe, a snapshot of reality when the cosmos was only about 380,000 years old. Pause for a moment and consider what that means. The photons reaching our detectors today began their journey before any star existed, before any planet existed, before any galaxy fully formed, before every living thing that has ever existed. They have traveled through almost the entirety of cosmic history. Yet relativity suggests something extraordinary. Those photons never experienced the journey. To us, nearly 14 billion years separate their emission from their detection. To the photons, no time passes at all. This is one of the most difficult ideas to truly absorb because our intuition is built around duration. We imagine age as something accumulated through time. A person becomes old because years pass. A star becomes old because billions of years of nuclear fusion occur. Age seems inseparable from history. But photons reveal that history and age are not necessarily the same thing. The cosmic microwave background appears ancient from our perspective because we occupy one endpoint of an enormous temporal interval. The photons themselves occupy a different relationship with reality. The billions of years belong to the universe, not to them. Imagine receiving a message in a bottle carried across an ocean. The bottle may spend decades drifting through storms and currents before finally reaching shore. To you, the journey appears long. Entire generations may pass while the bottle travels. Yet now imagine that the bottle somehow experiences no passage of time during its voyage. Departure and arrival become directly connected. The decades disappear from its perspective. Something similar may be happening with the oldest light in existence. This realization creates a fascinating tension between two ways of viewing reality. From one perspective, the universe possesses a history. Events unfold. Galaxies evolve. Stars are born and die. Entropy increases. The cosmos ages. From another perspective, photons connect events across that history without participating in its passage. The oldest light in the universe remains forever tied to the moment of its creation, almost like a messenger stepping outside time while carrying information through it. The deeper physicists investigated this idea, the more profound it became. because photons are not merely passive travelers. They are how the universe reveals itself. Every image astronomers capture depends on photons. Every observation of distant galaxies depends on photons. Every measurement of the early universe depends on photons. In a very real sense, light allows the universe to communicate with itself across cosmic time. Think about what happens whenever you look at the night sky. You never see objects as they are now. You see them as they were when their light began traveling toward you. The moon appears roughly 1 second in the past. The sun appears 8 minutes in the past. Nearby stars appear years in the past. Distant galaxies appear millions or billions of years in the past. Astronomy is not merely the study of space, it is the study of time. Every photon carries history. Every photon is a message from another era. And yet those same photons may never experience the history they carry. The paradox feels almost poetic. The universe's greatest storytellers may exist outside the story. This becomes even more fascinating when we consider the enormous expansion of the cosmos. Since the release of the cosmic microwave background, the universe has expanded dramatically. Galaxies have drifted apart. Distances have increased. Entire structures have formed. The photons filling space today have been stretched by that expansion. Originally, they possessed far higher energies. Over billions of years, the expanding universe stretched their wavelengths until they became microwave radiation. This process is known as cosmological redshift. It is one of the clearest pieces of evidence that the universe itself is expanding. Yet even here, light reveals something strange. The photons change from our perspective. Their wavelengths stretch. Their energies decrease. The universe around them evolves. But the photons themselves never experience the passage required to witness that evolution. Again and again, we encounter the same theme. The universe changes. Light connects those changes. Yet light does not participate in time the way everything else does. And this leads us toward an even deeper question. If photons from the beginning of the universe remain forever connected to their origin, what happens to photons in the distant future? Will they continue traveling forever? Can light survive longer than stars? Longer than galaxies? Longer than black holes? What role will photons play when the universe itself begins approaching its final fate? Because the future awaiting light may be even stranger than its past. And in the next chapter, we will follow photons into the unimaginably distant future and discover why the last light in the cosmos may witness the end of everything we know. When we look up at the night sky, it is easy to believe that light is permanent. Stars appear to shine with a calm and ancient confidence, as if they have always been there and will always remain there, scattered across the darkness, like fixed points in the structure of reality itself. Even when we learn that stars are born and die, the universe still feels overwhelmingly filled with light. The sun rises every morning. The moon reflects its glow. Distant galaxies shine across billions of light years. Nebulae burn with color. Quasars blaze from the early universe with energies so extreme that they can outshine entire galaxies. Everywhere astronomy looks, photons are moving, spreading, carrying information, crossing the cosmic void. Light feels like one of the universe's most reliable facts. It is the thing that lets the cosmos reveal itself. Without it, the universe would still exist, but almost everything would be hidden. There would be no visible stars, no galaxies and telescopes, no colors, no images, no ancient signals arriving from the beginning of time. Light is the messenger, the memory, the evidence. It is how the universe speaks across distance. But the deeper we follow the story of time, the more unsettling the future becomes, because the universe that seems so full of light today is not guaranteed to remain that way. Stars are not eternal. Galaxies are not eternal. Even black holes, the darkest and most powerful objects in the cosmos, may not be eternal. If we travel far enough into the future, beyond every human scale, beyond every geological scale, beyond the lifetime of the sun, beyond the lifetime of galaxies, we reach a future where the universe becomes colder, darker, thinner, and quieter. And in that future, one of the strangest questions in physics begins to appear. What happens to light when almost everything that creates it is gone? To understand the last light in the cosmos, we first have to understand that every star is spending itself. A star looks stable from the outside because its life is so long compared to ours. But deep inside its core, it is constantly changing matter into radiation. Hydrogen fuses into helium. Energy is released. That energy slowly works its way outward through the star's interior, eventually escaping as light. Every photon that leaves a star is part of that star's long process of exhaustion. The sun feels endless because it has already shone for billions of years and will continue shining for billions more. But it is not endless. It is burning through a finite supply of fuel. One day, roughly 5 billion years from now, the sun will leave the calm main sequence phase of its life. It will swell into a red giant, reshape the inner solar system, shed its outer layers, and leave behind a white dwarf, a dense glowing remnant that slowly cools in the dark. The same basic truth applies everywhere. Massive stars live fast and die violently in supernovae. Smaller stars live far longer, fading over immense timescales. Red dwarfs, the smallest common stars, may burn for trillions of years, outlasting almost everything currently shining brightly in the sky. But even they are not eternal. A star is not a permanent lamp placed in space. It is a temporary engine. It shines because it is changing, and because time moves forward, every engine eventually runs down. Now zoom outward from a single star to the whole universe. Today, the cosmos is still in a bright era. Stars continue forming inside giant clouds of gas. Galaxies still contain material capable of collapsing under gravity and igniting nuclear fusion. The night sky, seen through powerful telescopes, is alive with structure and radiation. But this era is temporary. Over extremely long periods, the gas needed for new stars becomes less available. Some of it is locked away in stellar remnants. Some is blown out of galaxies. Some is heated or dispersed. Star formation gradually slows. Existing stars keep aging. The brightest stars disappear first because they burn their fuel fastest. Then smaller and smaller stars dominate the light of the cosmos. Eventually, after timescales so long that human imagination begins to fail, the universe enters an era where almost no new stars are born. The great stellar age fades. The universe becomes populated mostly by remnants: white dwarfs, neutron stars, black holes, cold planets, and objects drifting through an expanding darkness. If an observer existed in that far future, the sky would not resemble ours. The rich cosmic web of glowing galaxies would be fading. Many distant galaxies would have disappeared beyond the cosmic horizon because the expansion of space continues stretching the universe apart. Local stars would have died or cooled. The universe would still contain matter, but less and less of it would be producing fresh light, and yet photons would still be there. This is where the story becomes haunting. Light can outlive its source. A star may die, but the photons it emitted before its death continue traveling. A civilization may vanish, but the light reflected from its planet may continue crossing space for millions or billions of years. A galaxy may evolve beyond recognition, but the photons it released in an earlier age may still arrive somewhere, carrying a frozen record of what it once was. In this sense, light becomes the memory of the universe. It preserves appearances long after the objects themselves have changed or disappeared. When astronomers look at distant galaxies today, they are not seeing those galaxies as they are now. They are seeing the light that left them long ago. Some of the stars in those galaxies may already be dead. Some structures may have merged, collapsed, or transformed. The photon does not care. It carries the information from the moment of emission forward through spacetime. The universe may move on, but light keeps the past visible. It is almost like a cosmic echo, not an echo of sound, but an echo of form, temperature, motion, and history. This becomes even more extraordinary when we connect it back to the central idea of this video. From our perspective, a photon can be ancient. We can say that a photon from the cosmic microwave background has traveled for nearly 13.8 billion years. We can say that light from a distant galaxy began its journey before Earth existed. We can call some photons young and others old based on how long ago they were emitted. But for light itself, the idea of age becomes unstable. A photon does not experience the billions of years that we assign to its journey. It does not wait while stars evolve. It does not witness galaxies forming around it. It does not feel the long darkness between clusters. It does not grow older as the universe expands. The time belongs to observers like us, observers made of matter, moving slower than light, existing inside duration. The photon remains tied to a path where the passage of time collapses. This means that the last light in the cosmos may be unimaginably old from the perspective of the universe, while still being ageless in the strange relativistic sense. That contrast is one of the most beautiful and disturbing ideas in physics. The universe can age around light, while light itself remains untouched by aging. As the universe continues expanding, the fate of photons becomes even stranger. Space itself stretches, and as it stretches, the wavelengths of traveling photons stretch with it. This is cosmological redshift. A photon that began as energetic visible or ultraviolet light can be stretched into infrared, then microwaves, then radio waves with enormous wavelengths. The cosmic microwave background is the clearest example. Those photons were once part of a hot young universe, but cosmic expansion has stretched them into faint microwave radiation. In the far future, the same process continues. Photons drifting through an expanding universe lose energy relative to observers. Their wavelengths grow longer and longer. Light becomes colder, weaker, more diffuse. The universe does not need to destroy photons to make them fade. Expansion itself slowly drains their observable energy. A photon can continue existing, but becomes so stretched that detecting it becomes almost impossible. The light is still there in principle, but it becomes ghost-like, diluted across cosmic distance, its energy spread thinner and thinner by the growth of space. This means the future universe is not simply dark because stars stop shining. It is dark because old light becomes increasingly unreachable, increasingly red-shifted, increasingly weak. Imagine a final observer in the far future, living inside a gravitationally bound island of matter, perhaps a remnant galaxy cluster, long after most other galaxies have vanished beyond the horizon. To that observer, the universe might appear almost empty. The evidence that once revealed cosmic expansion, the Big Bang, and the large-scale structure of the universe could become nearly inaccessible. distant galaxies would have slipped away beyond observational reach. The ancient background radiation would be stretched to wavelengths so long and temperatures so low that it might be impossible to detect. The sky would not tell the same story it tells us now. The universe's memory would fade, not because the past never happened, but because the photons carrying that memory would be stretched, hidden, or forever beyond reach. Then come the black holes. For an almost incomprehensibly long time after stars have died, black holes may dominate the universe's remaining drama. They will sit in the dark, massive and cold, slowly consuming what matter remains nearby. Around them, ordinary processes will become rare. The universe will be quiet in a way we cannot truly imagine. Yet even black holes are not completely permanent according to quantum theory. Stephen Hawking discovered that black holes should emit radiation, now known as Hawking radiation. For stellar mass and supermassive black holes, this radiation is incredibly weak, far colder than the current background of the universe. Today, it is practically impossible to observe directly. But in the far future, as the universe cools and black holes have nothing left to feed on, Hawking radiation becomes their slow path toward disappearance. Over absurdly vast timescales, black holes lose mass. The smaller they become, the warmer they get. Eventually, after durations so enormous that they make the current age of the universe seem like less than a blink, black holes evaporate. And when they do, they release radiation. Photons again appear near the end of the story. There is something almost circular about this. Near the beginning of the observable universe, the oldest light was released when the cosmos became transparent. Near the end of the universe, some of the last significant light may come from the evaporation of black holes. Between those extremes, stars shine, galaxies glow, planets reflect, life sees, telescopes observe, and photons carry history from one place to another. Light is there at the beginning of visibility, and there again near the final fading of structure. It connects the hot early cosmos to the cold future cosmos. It is present when atoms first allow radiation to travel freely, and it is present when the last great gravitational objects slowly dissolve into quantum radiation. And through all of this, the photon remains strange. It does not age like matter. It does not experience cosmic history the way we do. It can be born in a fireball, stretched by expansion, delayed by gravity, bent by spacetime, absorbed by matter, or emitted by dying black holes. Yet its own relationship with time remains unlike anything else in the universe. This is why the last light in the cosmos is more than a poetic image. It forces us to confront what time really means. If the universe eventually becomes a place where almost nothing changes, where entropy approaches its maximum, where energy is spread thinly and no complex processes remain, does time still have meaning in the same way? Time, for us, is tied to change. We measure it with motion, decay, memory, growth, and transformation. But in a universe approaching heat death, meaningful change becomes rarer and rarer. Events become separated by unimaginable durations. The arrow of time continues in principle, but its visible consequences fade. Photons may still drift through the dark, but there may be no eyes to see them, no detectors to record them, no civilizations to interpret them. Light without observers becomes a strange thing to contemplate. It may carry information, but information only becomes meaningful when it can be received. In the far future, the cosmos may be filled with messages that no one is left to read. And yet, even this final darkness does not make light meaningless. In fact, it reveals why light is so central to the story of existence. Every photon is a connection between events. It links an emission to an absorption, a source to a destination, a past condition to a future observation. The last photons of the universe would be the final threads of that connectivity, stretched across a cosmos that has lost almost all structure. They would be the faintest remaining bridges between what once happened and whatever remains. The universe may become cold, but light preserves traces. The universe may become dark, but photons continue to define what can still be known. The universe may lose its stars, but radiation remains as the final language of physics. So when we ask whether light has a past or a future, the answer becomes layered. From our point of view, light has one of the richest histories imaginable. It comes from stars, galaxies, black holes, and the early universe. It travels across cosmic time. It records the evolution of everything visible. It may continue into the far future, long after its source is gone. But from the light's own strange relationship with spacetime, the usual categories of past and future collapse. The photon does not remember the star. It does not anticipate the detector. It does not wait through the long expansion of the universe. It simply connects. And perhaps that is the deepest role of light. Not to live through time, but to bind time together. Not to age, but to carry age. Not to experience history, but to make history visible. In the next chapter, we will move even deeper into that idea, exploring why light may be less like a traveler moving through the universe and more like a thread woven through the structure of reality itself, connecting moments that seem separated to us, but may be far more unified than our slow, time-bound minds can easily understand. By this point in our journey, light no longer resembles the simple phenomenon most of us learned about in school. We began with the familiar idea of light as something that illuminates the world around us. We followed photons across interstellar space. We discovered that they occupy a unique relationship with time. We saw that they do not age in the ordinary sense. We watched them escape dying stars, travel through expanding space, reveal the history of galaxies, and carry messages from the earliest observable moments of the universe. Again and again, the same pattern emerged. Every time we tried to place light into a simple category, it slipped away. It was not merely a particle. It was not merely a wave. It was not merely a traveler moving through space. The deeper we looked, the more it seemed as though light occupied a special position within reality itself. And this raises a remarkable possibility. What if photons are not simply moving through the universe? What if they are helping connect it? At first, this idea sounds more philosophical than scientific. We are accustomed to imagining reality as a collection of separate objects. Stars exist in one place. Galaxies exist in another. People live on planets. Planets orbit stars. Everything appears divided by enormous distances. Space itself seems responsible for that separation. If something lies a million light years away, we naturally think of it as distant, disconnected, almost unreachable. Yet physics repeatedly reveals that separation is not as simple as it appears. The universe is filled with relationships. Gravity links objects across vast distances. Quantum mechanics introduces forms of correlation that seem almost impossible according to ordinary intuition. Information moves continuously from one region of reality to another, and throughout all of these processes, light plays a central role. Photons are constantly carrying information across the cosmos, connecting events that would otherwise remain isolated. Without light, much of the universe would become inaccessible, not merely hidden, but disconnected. The stars would still burn, galaxies would still rotate, black holes would still consume matter, yet the relationships linking those events would vanish from our perspective. Light does not merely reveal the universe, it creates pathways through which different regions of reality become aware of one another. Think about what happens every time you look at the night sky. It feels like a simple act. You raise your eyes and see stars. Yet hidden inside that ordinary experience is an extraordinary chain of connections. Photons leave the surface of a star. They travel through interstellar space. Some pass through clouds of gas and dust. Some curve around massive objects because gravity bends space-time. Eventually, a tiny fraction reach Earth. They enter your eyes. They interact with molecules inside your retina. Electrical signals move through your nervous system. Your brain processes the information. Conscious awareness emerges. A star that may be hundreds or thousands of light years away becomes part of your experience. The event occurring within the star and the event occurring within your mind become linked through light. Without photons, that connection never forms. The star remains physically real, but the bridge between the star and the observer disappears. This idea becomes increasingly profound as we move from individual stars to the universe as a whole. Modern astronomy is possible because photons connect us to distant places and distant times. Every image captured by a telescope represents a relationship established through light. When astronomers observe a galaxy billions of light years away, they are not traveling there physically. They are receiving photons. The information carried by those photons allows the galaxy to become part of human knowledge. Light transforms separation into connection. The farther we look, the more obvious this becomes. Entire fields of cosmology depend upon photons that have been traveling for billions of years. The cosmic microwave background exists because ancient light continues connecting the present universe to its earliest observable era. In a very real sense, photons allow different moments in cosmic history to communicate with one another. And yet, as remarkable as this sounds, modern physics hints at something even deeper. Over the past few decades, a growing number of physicists have begun suspecting that information may be more fundamental than matter itself. This idea emerged from several directions at once. Black hole physics revealed that information plays a crucial role in understanding gravity. Quantum mechanics revealed that information behaves in surprisingly physical ways. Entropy turned out to be deeply connected to information. Again and again, theories that appeared unrelated began converging on the same conclusion. Information is not merely a description of reality. It may be part of reality's foundation. If this is true, then photons become even more important than we imagined, because photons are among the universe's primary carriers of information. Every photon tells a story about where it came from. A photon leaving a star contains information about the temperature of that star. A photon leaving a galaxy contains information about the motion of that galaxy. A photon from the early universe contains information about conditions billions of years ago. Every beam of light acts like a messenger traveling through space-time. And when billions upon billions of photons move through the cosmos, they create an immense network of informational relationships connecting different regions of reality. Imagine the universe not as a collection of isolated objects floating in emptiness, but as a gigantic web of connections. Every star linked to every observer through photons. Every galaxy linked to every telescope through photons. Every era of cosmic history linked to every future observer through photons. Suddenly, reality begins looking less like a collection of things and more like a network of relationships. The objects remain important, of course, but the connections between them become equally significant. Light becomes the mechanism through which those connections are established and maintained. This perspective becomes especially fascinating when combined with quantum mechanics. One of the strangest discoveries of the 20th century was quantum entanglement. Two particles can become linked in such a way that their properties remain correlated even when separated by enormous distances. Einstein famously disliked this implication and referred to it as spooky action at a distance. Yet decades of experiments confirmed that entanglement is real. Nature genuinely allows relationships that seem to transcend ordinary notions of separation. At first, physicists treated entanglement as a bizarre feature of microscopic systems. More recently, however, some researchers have proposed something far more radical. They suggest that spacetime itself may emerge from networks of quantum relationships. Pause and think about what that means. We usually imagine space as fundamental. Objects exist because space provides a place for them to exist. Distance exists because space separates locations. Motion exists because objects move through space. But what if that picture is backward? What if space emerges from deeper relationships? What if the connections come first? In certain modern theories, geometry itself appears linked to patterns of information and entanglement. The universe starts looking less like a stage and more like a network. Distance becomes something that emerges from relationships rather than something existing independently. And once again, light seems to occupy a special position within the story. Photons carry information. Photons create connections. Photons link events across spacetime. If reality is fundamentally relational, then light may be one of the primary mechanisms through which those relationships become visible. This idea also sheds new light on something we discussed earlier, the strange timelessness of photons. Throughout this series, we have repeatedly encountered the fact that light occupies an unusual relationship with time. Photons do not age in the ordinary sense. Their journeys connect events separated by billions of years without requiring billions of years of experience duration. At first, this seemed like an isolated curiosity of relativity, but perhaps it is part of a larger pattern. If photons exist at the boundary where ordinary temporal concepts begin breaking down, then perhaps their role as connectors is not accidental. Perhaps light appears timeless because it participates in something deeper than the temporal flow experienced by matter. Human beings live inside duration. We remember the past. We anticipate the future. Our identities are built from sequences of experiences unfolding through time. Photons appear different. They connect events without sharing that experience of duration. In a sense, they weave together different regions of spacetime while remaining detached from the passage that separates those regions for us. This is why light feels increasingly mysterious the more closely we examine it. The photon is both ordinary and extraordinary. It is everywhere. It surrounds us constantly. Yet it also occupies a unique position at the edge of some of physics' deepest questions. The universe itself seems almost built around light. Relativity revolves around the speed of light. Astronomy depends upon light. Cosmology depends upon light. Our understanding of distant galaxies depends upon light. Even our understanding of time depends upon light. Again and again, whenever physicists push toward the foundations of reality, photons appear waiting there. Not necessarily because they contain all the answers, but because they reveal where our assumptions begin breaking down. Perhaps that is why light has fascinated humanity for so long. Long before physics existed, people associated light with knowledge, understanding, and revelation. Ancient cultures used it as a symbol of truth. Philosophers treated it as a metaphor for awareness. Scientists eventually transformed it into an object of rigorous study. Yet despite centuries of progress, the symbolism never completely disappeared. Light still reveals hidden things. It still uncovers deeper layers beneath appearances. It still acts as a bridge between ignorance and understanding. And perhaps nowhere is that more evident than in our current exploration. We began with a simple question about whether light has a past or a future. Along the way, that question expanded into something much larger. We discovered that photons occupy a strange relationship with time. We discovered that they may be effectively ageless. We discovered that they preserve the history of the universe while remaining detached from the passage of history themselves. We discovered that they carry information across cosmic distances and may even help reveal the deeper structure beneath spacetime. But our journey is not over yet, because there remains one final mystery more profound than any we have encountered so far. If photons do not experience time the way we do, and if they help connect distant regions of reality, then what does that tell us about the universe itself? Could it be that our everyday experience of past, present, and future is only one layer of a much deeper structure? Could reality be organized in a way that transcends ordinary temporal flow altogether? In the next chapter, we will confront that possibility directly and explore one of the most astonishing ideas ever suggested by modern physics: that the universe may not fundamentally exist as a story unfolding through time, but as a timeless structure in which light reveals connections that have always been there. For almost your entire life, time has probably felt like the most obvious thing in existence. Every experience you have ever had seems to confirm the same simple picture. The past is gone. The future has not happened yet. The present sits between them, moving steadily forward like a spotlight traveling across an endless landscape. Moments arrive, exist briefly, and then disappear forever. Childhood becomes adulthood. Tomorrow becomes today. The future transforms into the past. Everything appears to unfold in a continuous flow. We become so accustomed to this experience that questioning it feels almost absurd. After all, what could be more real than the passage of time itself? And yet, throughout this journey, light has repeatedly challenged that intuition. Again and again, photons have forced us to confront possibilities that seem almost impossible to reconcile with ordinary experience. We discovered that light does not age. We discovered that time collapses along the paths traveled by photons. We discovered that events separated by billions of years can be connected by light without requiring billions of years of experience duration. We discovered that the oldest photons in the universe may be forever linked to the moment of their creation, despite traveling across nearly the entire history of the cosmos. Every chapter has pointed toward the same unsettling conclusion. Perhaps the universe does not fundamentally work the way it appears to us. Perhaps past, present, and future are not as absolute as they seem. This possibility emerged most clearly through Einstein's theory of relativity. Before Einstein, time was generally viewed as universal. The entire universe shared a common clock. The present moment stretched across reality like an invisible sheet connecting everything that existed. Events happened in a single sequence. There was one past, one present, and one future shared by everyone. It felt obvious because it matched everyday experience. Relativity shattered that picture. Observers moving at different speeds experience time differently. Clocks tick at different rates depending on motion and gravity. events that appear simultaneous for one observer may not appear simultaneous for another. The deeper physicists explored these consequences, the more difficult it became to maintain the idea of a universal present. Eventually, a remarkable realization emerged. The equations of relativity do not contain a special now. They describe spacetime as a complete structure. Past events occupy locations within that structure. Future events occupy locations within that structure. Everything exists as part of a larger geometric whole. Nothing inside the mathematics identifies a single moment as objectively present. This realization led to one of the most fascinating interpretations in modern physics, the block universe. According to the block universe view, space-time resembles a complete landscape rather than a story being written page by page. Every event occupies its place within a four-dimensional structure. Your birth occupies one region. This moment occupies another. Future moments occupy additional regions. The history of stars, galaxies, civilizations, and observers all become part of the same space-time architecture. Imagine holding a novel in your hands. The beginning exists. The middle exists. The ending exists. A reader experiences the story sequentially, moving from page to page and creating the sensation of progression. But the book itself already contains every chapter. The ending is not waiting to be created. It already occupies its place within the structure. Some physicists believe reality may be similar. The sensation of time flowing could emerge from the way conscious observers experience space-time rather than from space-time itself. At first, this idea sounds deeply counterintuitive. Human beings feel time passing. The experience seems undeniable. Yet relativity repeatedly suggests that our intuitions about time may be limited by the perspective from which we observe reality. We are creatures moving slowly through space-time. We occupy a very specific relationship with the universe. What feels fundamental to us may actually be emergent. This is where light becomes especially important. Throughout our exploration, photons have repeatedly occupied the boundary where ordinary temporal concepts begin breaking down. A photon does not experience the universe the way we do. It does not accumulate memories. It does not anticipate future moments. It does not move through time in the familiar sense. Instead, photons appear to connect events across space-time directly. Their existence hints at a deeper structure beneath our ordinary experience of temporal flow. Imagine a photon emitted from a galaxy 10 billion light-years away. To us, the journey spans an enormous stretch of cosmic history. Entire generations of stars live and die while the photon travels. Galaxies evolve. Black holes grow. The universe expands. Yet relativity suggests that the photon does not experience this progression. The departure and arrival remain connected without an experienced interval. Think about how strange that really is. The universe ages. The photon does not. History unfolds. The photon does not witness its unfolding. Billions of years separate two events. The photon experiences no billions of years. Again and again, light hints that temporal separation may not be as fundamental as it appears. And this brings us to a profound possibility. Perhaps reality is not fundamentally divided into past, present, and future. Perhaps those distinctions emerge from the way conscious beings interact with space-time. Consider your own experience for a moment. You remember the past because your brain contains records of previous events. You do not remember the future because those records do not exist. Memory creates an asymmetry. Information points backward. Expectations point forward. The result is a powerful sensation that time flows in one direction. But what if this sensation emerges from information rather than from the fundamental structure of reality? What if consciousness functions like a spotlight moving through an already existing space-time landscape? The idea sounds extraordinary, yet modern physics repeatedly nudges us toward possibilities like this. Some researchers suspect that time itself may not be fundamental. Instead, time may emerge from deeper informational relationships. Space may emerge from such relationships as well. At the deepest level, reality could consist of networks of information, connections, and correlations from which space-time arises as a large-scale phenomenon. If this is true, then our familiar picture of reality undergoes a dramatic transformation. The universe stops looking like a movie playing frame by frame. It starts looking like a structure, a vast interconnected architecture, a complete pattern. Light becomes especially important within this picture because photons help reveal those connections. They link distant regions of space-time. They transfer information. They preserve records of ancient events. They act as bridges between different parts of the cosmic structure. In a sense, photons make the universe visible to itself. And perhaps that is why they occupy such a unique position in modern physics. Whenever we investigate the deepest questions about reality, photons appear. Questions about space-time lead to light. Questions about relativity lead to light. Questions about cosmology lead to light. Questions about information lead to light. Again and again, photons seem to stand at the boundary between the world we experience and the deeper reality hidden beneath it. The more we examine them, the more the universe begins looking less like a collection of separate moments and more like a unified whole. Imagine standing outside a mountain range and viewing every peak simultaneously. The traveler moving through the mountains experiences one view at a time. The landscape unfolds gradually. New sights appear while old sights disappear. Yet from above, the entire structure exists at once. Perhaps consciousness resembles the traveler. Perhaps space-time resembles the landscape. Perhaps the flow of time emerges from movement through that landscape rather than from the creation of reality itself. Light, with its strange relationship to time, may be one of the strongest clues pointing toward this possibility. And yet, even after everything we have explored, one final question remains. If photons connect the entire history of the universe, if light reveals relationships transcending ordinary temporal separation, if reality itself may be deeper than past and future, then what does that ultimately tell us about existence? What does it mean for a universe where the fastest messenger appears detached from time? What does it mean for beings like us, whose lives are built entirely from time? And what does it mean for the deepest mystery of all, the relationship between consciousness and reality itself? As we approach the final chapter of our journey, we will bring together everything we have learned about light, time, information, and space-time. We will step back and examine the larger picture emerging from modern physics. And in doing so, we may discover that the question we started with, whether light has a past or a future, points towards something far greater than photons alone. It points toward the possibility that reality itself is far stranger, far more connected, and far more timeless than we ever imagined. As we come to the end of this journey, it is worth returning to the question that started everything. Does light have a past? Does light have a future? At first, the answer seems obvious. Of course it does. Every photon is emitted from somewhere. Every photon travels through space. Every photon eventually arrives somewhere else or interacts with matter along the way. We naturally imagine light moving through time exactly as everything else does. A photon leaves a star, spends years, centuries, or billions of years crossing the universe, and eventually reaches its destination. That picture feels intuitive because it matches our experience. But throughout this exploration, we discovered something remarkable. The universe does not seem to agree. Again and again, relativity pushed us toward a strange conclusion. As velocity approaches the speed of light, the passage of time begins shrinking. Distances contract. The familiar separation between events starts dissolving. And at the limit occupied by light itself, something extraordinary happens. The concepts we rely upon, duration, aging, waiting, even the distinction between before and after, become increasingly difficult to define. A photon emitted from a distant galaxy may spend billions of years traveling from our perspective. Yet those billions of years belong to us, not to the photon. The universe ages around light. Stars evolve around light. Galaxies transform around light. Civilizations rise and fall around light. But the photon itself remains tied to a path where ordinary temporal experience disappears. This realization forced us to rethink some of our deepest assumptions. We discovered that light may be effectively ageless. We discovered that the oldest photons in the cosmos, including those released shortly after the Big Bang, remain connected to their origins in ways that challenge our intuition. We discovered that photons carry the history of the universe without participating in that history as we do. They preserve information, they connect events, they act as bridges between distant regions of spacetime. In many ways, light became something more than a traveler. It became a clue about the structure of reality itself. Because every time we followed light deeply enough, we arrived at questions larger than photons, questions about spacetime, questions about information, questions about consciousness, questions about whether the flow of time is truly fundamental or whether it emerges from something deeper. The universe began looking less like a sequence of isolated moments and more like an interconnected structure, less like a story being written page by page, more like a vast pattern whose pieces are linked together by relationships we are only beginning to understand. And perhaps that is why light has fascinated humanity for so long. Long before modern physics existed, people associated light with revelation, understanding, and truth. It became a symbol of knowledge because it revealed hidden things. Today, after centuries of scientific discovery, that symbolism feels strangely appropriate. The more we study light, the more it continues revealing hidden layers of reality. Not because photons contain magical answers, but because they sit at the crossroads of some of the deepest mysteries in existence. Relativity points toward light. Cosmology points toward light. Quantum mechanics points toward light. The origin of the universe points toward light. The fate of the universe points toward light. Again and again, the same messenger appears. And perhaps the most beautiful part of all this is that the mystery remains unfinished. We still do not possess a complete theory uniting quantum mechanics and gravity. We still do not fully understand how space-time emerges. We still do not know whether time is fundamental or emergent. We still do not know why the universe possesses the exact structure that it does. The deeper we explore, the more questions appear. Yet that is not a weakness of science. It is one of its greatest strengths. Every answer reveals a deeper horizon. Every discovery opens a new mystery. Every photon arriving from the darkness carries another piece of a puzzle that humanity is still assembling. Tonight, somewhere in the universe, a photon is leaving the surface of a star. Somewhere else, another is escaping the edge of a distant galaxy. Ancient photons from the early universe continue crossing the cosmos after nearly 14 billion years. of travel. Light from stars that no longer exist is still moving through space. Messages from the past continue arriving in the present. Connections continue forming across unimaginable distances. The universe is still speaking, and light is still carrying the message. Thank you for joining me on this journey through relativity, cosmology, spacetime, and the strange, timeless nature of photons. If you enjoyed this exploration, consider subscribing to Science Sleep Theory for more calm, immersive journeys into the deepest questions in physics, astronomy, and the hidden structure of reality. Until next time, keep looking deeper, keep wondering, and as ancient starlight continues its endless journey across the darkness, sleep well.